Hello everyone, and welcome back to a new video in programming the finite element method using MATLAB. In the previous video, we kind of fixed some issues in the code. However, there are still some issues remaining. But to fix those issues, I think it's best to start with the post-processing and finalize it, and then fix the issues in the code, because post-processing would give you a better way of seeing data rather than double-clicking on the controller and scrolling for the data. It's kind of tedious. So I think it's best to shift the debugging or benchmarking session, where I will be using Robot, by the way, benchmarking session at the end of the series, and focus now on completing the code and kind of improving the data presentation of this piece of code. So, of course, I want once again to give the reminders that this is part of a video series about the FEM theory, linked top right, and its own programming series linked also on the top right. And I also want to emphasize that the channel members have access to the entire source code. However, if you are not a channel member, then don't worry, because the entire code will be written in front of you, so you can be able to write along with me and you will have the exact same code as mine. So basically today we are going to put the groundwork for the post-processing system, and with that being said and without further ado, sit back, relax and enjoy the show. Okay, now performing linear elastic analysis includes also the post-processing. Now some of you like to call controller.perform post-processing, and some of you like to keep the post-processing as part of the linear elastic analysis. I'm not really sure. I think I will keep it as part of the linear elastic analysis, because my opinion is that the linear elastic analysis should also include the post-processing, as it comes kind of along with the analysis. So I think that it should be in the linear elastic. Let me just stop all those discretization things. Let me just remove those discretizations. So let me just run again the main. I will basically have this. I think also I need to remove the release if I have it. So let me just check if I define the release. Yep, let me remove it first. So I think now we are back to our frame that is double fixed with a certain distributed load, just to make sure that we are on the same page before we embark on the post-processing system. So let me go to main here and run it and see what happens. Yeah, so now we have the double fix and it seems fine. Okay, now we need to start programming our post-processing system. So I'll comment out the viewer because I don't want to keep viewing it. And now I'm gonna go to the STR controller, which is somewhere here. And in the STR controller, I will define my post-processing system. Now my post-processing system are going to be part of the analysis. So when you go to the analysis, structural analysis region, you can see here that the perform post-processing is already inside, but the perform post-processing is an empty function, which needs to change. So if we go to perform post-processing here, you can see it's a totally desolate and empty function, and that's what we are here to change today. So in my post-processing systems, there are multiple things I'm gonna do. First, I'm gonna init post-processing systems. Here, this is usually what I do. If I have a matrix that needs to be defined or something, I like to initialize my stuff here. Secondly, I'm gonna calculate the local displacements and forces on each element. Maybe I should put an A capital here. In that case, I have the displacements of the nodes in the global sense, but I need, of course, to find the displacements in the local sense of the elements to find the forces in the local sense, because I want later to calculate bar internal forces and displacements. So in the end, my goal is to calculate the shear force diagrams and bending moment diagrams and all those cool diagrams for those elements once we're done, okay? But of course now we cannot do that, so let's start step by step. We cannot do that because we don't have the local displacements on the beams. That's something that we will change in the upcoming videos. So here, of course, I'm gonna call in the object dot because I'm gonna program this in the controller. Now, of course, I get an error because the controller doesn't include those things, which means I need to make the controller include them. Now, I am going to put here the region. So I'll say here post. I don't think that's correct. I don't think that's good, because I'm following the system. So here, prepare has a region, solve has a region, generate has a region. Yeah, the region here should be in the end, right? Yeah, in the end. So let's go here, push the enter key, and define as a region here. I'll call this post-processing functions here. So here, all the stuff that is in the post-processing is going to take place here. So let's do it now. I forgot what the function names are. Let me just check. Init, post-processing. Okay, so function. I think I will return void. Nothing will happen here. And init, post-processing systems. That is basically with an object here. So that's the function. Now the first error has subsided. I can just Control-C this and Control-paste it here. So function, Control-paste, object, and end. And of course, the last one, let me copy it very quickly. There we go. Function, the name, object, and end. Okay, so now we have the post-processing functions here. And now it's time to define those functions. I will start with init post-processing systems. Now, what are we going to do in the initialization of post-processing systems? I'm going to give the reactions for the str node, right? So let me see something very quickly. Where is the str node? There are the str nodes. Yep. Did I define something for the reactions? No. Because reactions are one of the quickest way to debug stuff. I don't have the reactions yet. I have the deflections. So I need something that captures the reactions. So I think what I can do here is I can basically ask or define reactions here or put reactions here. And then the reactions, of course, are calculated during the post-processing system. So when we initialize the post-processing system, I also need to initialize the reactions, at least for now. So here I will run through all the nodes, the str nodes in this case. Now here I would need something called the load case count. So load case count. That's easy. This equals the object or length of the object of the str load cases. This is load case count. Then I'm going to go for a for loop for I equals from 1 to, call it node index, just to kind of make more sense. From 1 to the length of the object.str nodes, because we are saving the str nodes in the controller. And here I'm going to fish out the node. Node equals object.str nodes at the node index. And now I'm going to define or initialize it. So node.reactions equals zeros off. Now here, once again, I want to remind myself that I will do it similar to the deflections, in which I am going to have the load cases be rows and the degrees of freedoms be columns. Yeah, I think I'll do that. So let me just put it here because I might forget it in the future. I just go here and remind myself rows are load cases, columns are DOFs. Just to remind myself what this is. So here node reactions equals zeros. I'm going to put in the load case count, and the degrees of freedom is 6, by the way. It's a magic number. I don't like using magic numbers, but I think degree of freedom 6 is something that I can keep everywhere. So yeah, I think so far this is what we want to initialize in the post-processing system. Maybe I'm going to initialize other things in other places, but for now, that's good as gold. Now, let's continue. So we finished at least the initialized post-processing systems. Now we go into something called calculate local displacements and forces. This is not going to be hard and not going to be easy too. We need to focus now. Let's get the number of load cases. So number of load cases. I mean, you can see me using different names sometimes. It doesn't matter because this is inside the scope of the function. I should be more consistent and use the same naming convention, but I don't know. It's not a wild thing, right? Now here degree of freedom is equal 6 because I want to avoid using magic numbers. Maybe I should write here DOF equals 6 and then write here DOF. We call them magic numbers because they just appear and have no meaning. But however, if you say DOF, then you know that you are having degrees of freedom here. It kind of makes more sense. Okay, so now we need to go through every single fembar. The moment diagrams are going to be related to the fembars, not to the stair lines, because it's the fembars that have been discretized. So now I need to go through every single fembar. So for fembar index, from 1 to the length of weight, I have fembar beams and fembar springs. I think I will just do it for fembar beams for now. Or maybe I should put it for both. You know what? Let's do it for both, and then maybe comment something out if I don't want it. So maybe I should do it for fembar springs and fembar beams. I will do it for both. So here, let's start with object.fembar springs. Okay. And we're going to do some stuff here for that thing. And we're going to do the same thing for the fembar beams. This is copy-pasting of code, which is something I despise because it makes maintenance of the code harder. That's why, once again, I'm really regretting not making inheritance here. It would make my life much easier. Okay, so let's do it for the fembar beams and then copy-paste for the fembar spring. Okay, so what do I have here? Let's fish out the fembar first of all. So here, I'm going to go for object, so basically right here, fembar. This equals object.fembar beams of fembar index. Now the same thing will apply in the spring with one difference, that here I'm going to fish out from the fembar springs. The rest of the code should be the same, I think. Or IDs, this equals fembar.femnode1.id and fembar.femnode2.id inside two cool brackets and a semicolon. So now we have the serial numbers of the IDs. What are we going to do with that? A lot of things, actually. Here, for every fembar, I must cycle through the load cases. So for I equals 1 to the length of no, I have it already. For 1 to number of load cases, I'm going to cycle through those things. I think the easiest way of doing things is to have the global displacement matrix open. I will check out what the serial number of the ID is, fish out the displacement from the global displacement matrix at that specific load case, and fill it into a vector. Now the vector needs to be initialized. Since it's two serial numbers, the vector is going to have 12 elements because 2 times 6 is 12. So what I think I should do is that whenever I go to a fembar, I should initialize the global displacement. I'll call this global displacement. That's zeros. I'll initialize it as a column vector. Here, I'm going to initialize global displacements. That's zeros. And the number of rows is going to be degree of freedom multiplied by 2, the number of nodes, or just length of serials if I want to avoid using magic numbers. Here, because it's a row column, this means that the number of columns is 1, because the rows are going to be the ones that have values. And maybe I'm even mistaken, because maybe here I want to have multiple load cases. And if I want to have multiple load cases, this would mean I would have to initialize it to a number of load cases. This becomes a matrix, by the way, but I will see what happens later if I have multiple load cases. For now, I think that's as good as gold. So now we need to cycle through each load case, and I need to keep track of where I am, because I'm going to fill the global displacement one by one, meaning I need an index for this, which is 1, and I will pass in the index whenever I add something to the global displacement. I will go in for a loop now. So for j equals from 1 to the length of the serials, or serial numbers. And now I'm also going to go for k equals from 1 to the degrees of freedom. And let's see what we can do now. So here, for femnode ID, this equals serials of j. Just fish it out now. I have the femnode ID. Now I need to get, maybe I should fish it out here to kind of preserve my calculations. Here, I don't want to blunder my degree of freedom. I will say global displacement at the index, because I'm filling it out, and at the load case I equals the object global displacement. Here, I'm going to take the let me just open here parentheses, femnode ID minus 1 multiplied by degrees of freedom. I'm not going to blunder this time. I'm going to add to it k. Wait, there is an I here. Yep. Now here I need to be very careful. So if the node is ID 1, this means it should start 1, 2, 3, 4, 5, 6. And if it's 2, it should be 7, 8, 9, 10, 11, 12. So let's consider it 2. If it's 2, it comes here. 2 minus 1 is 1. Multiplied by 6 is 6. And then it starts 7, 8, 9, 10, 11, 12. Yeah, I think that's right. I think we're doing good. Because I filled something in the global displacement, I'm going to increment the index. You cannot say plus plus here, we are not in C#. I think that's how I can find the global displacements. Now by the end of this, the global displacement should be 12 rows and X columns, where X is the number of load cases I have. I need to start calculating things. Local forces equals local stiffness matrix multiplied by local displacement. So that's the reason why we need to find the local displacements and then the local forces, and then later we can derive our diagrams. First of all, I need to find the local displacement and store it. So here in the fembar dot local displacement matrix, this is going to equal the fembar dot transformation matrix multiplied by global displacement. And fembar dot local force matrix, this is going to equal the fembar dot local stiffness matrix multiplied by the fembar dot local displacement matrix. Now I'm worried that I don't have those two things defined. This and this may not be defined in fembars before. So let's check if I define them or not. Fembar spring. Let's see what is defined there. Okay, yeah, local displacement and local force are indeed defined. Good for me. Good thinking back then. Also here? Yeah, also here. So, wait, what? Properties? Yeah, they are also here defined. Fine. So there is no error and there is no problem. Now, I think this should be cool. Let's see what else do I have to do. I think I should do the same thing for the fembar beams, springs, sorry. So all I have to do is to copy this entire thing and basically paste it here. I'm copy pasting code. That's bad programming habits. But I did not use inheritance, so I deserve what happens to me. This should give you the local forces at the start and the end of the fembars. Of course, those also include the equivalent nodal nodes, which means later when I do post-processing, I need to subtract the equivalent nodal nodes. But well, let's test it out and see if it even works. I'll go to main, click the run button, and of course I will get an error, right? Yeah, I get an error. Of course I do. Since when do I have an error here? This is new. This never happened before. Okay, let me put... Wait. Who is calling fembar beam here? How do you isolate faults? This is the newest stuff I have written. So the error must be in the newest stuff I have done. Because previously there was no error. So let's run and see what happens. I'm not asking for fembar beam to run. What are you talking about? I'm asking for main to run. My MATLAB is still crazy. Okay, I'll write it here, main. Okay, what's now? Unrecognized stir node? Oh, I called it reactions with an S. I need to remove the S. Or I need to add it. So I'll add it here and run the main again. Okay, so far so good. Let me remove this and see what happens now. Run. There are no errors. Yeah, there are no errors. So it seems it was not really a big thing. Now, I don't know about the logic behind it. There might be bugs, but at least programmatically speaking, it doesn't explode in my face, which is the first step of writing a program. But we started strong by initializing post-processing systems and by calculating local displacements and forces. But now we will continue with this, and that's something for another video. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a local-sized shout-out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support to the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel. I will catch you in the next video. Bye bye.